Hello everyone, welcome back. Till now we have solved problems where the back pressure outside the nozzle was brought down from P0 all the way down to third critical pressure. Till yesterday we have done up to that point. That is, we also took care of over expanded flow. Now we will go for the remaining portion. Only thing left is under expanded flow. Okay. When we think about under expanded flow, what do we mean? We go back to the plot again. I am going to say that P by P01 if I plot, then I am going to get something like this. This is my P critical 1. If there is a shock at the exit, and that becomes P critical 2. This is my P critical 3. Everything is divided by P01. Okay. So now we want to solve the cases where the pressure is below this P critical 3. Initially we said the flow changes inside the nozzle itself up to P critical 2. After that we solved yesterday last class where we did this between these two cases, and of course we went up to a point where we said those oblique shocks that are forming at the exit finally become Mach waves, the weakest oblique shocks ever possible. Okay. We have gone up to a point where it becomes the weakest oblique shock ever possible, and that just completes to become a Mach wave. Now we are going to start from that point, and I am going to say I have a nozzle exiting exactly parallel walls, that is just for simplification, and then I am going to say I just barely have a Mach wave there. This is the condition I have. This is my Mach wave, and I am going to say this pressures are equal on both sides, outside and the exit, which means my jet will just go straight. There will be no difference. Jet will just go straight. Okay. Now, if I decrease the pressure here, what should happen? Then the P exit is more than the outside pressure, which means it has not yet expanded to that value. So that is why this is called the under expanded region. That pressure is the under expanded pressure region, which actually means, by definition itself, I am going to say it is under expanded means it still needs to expand more, right? It has not yet expanded fully. What should happen? It should form an expansion fan around this corner, starting from the first point where there should be a change, which is that exit point where it first meets the outside world where there is a different pressure. So at that point it is going to send out some set of expansion waves, and what should be the very first wave? Same as this particular wave you already drew, right? It should be the same wave, because the first wave in an expansion wave is the same Mach wave. It will all be the same. Okay. So your expansion oblique shock that was inside just came out slowly and then became your Mach wave. After that, if I keep decreasing my back pressure, then it is going to continue from there and send out expansion waves that way. Okay. Now I will have a set of expansion fans like this. When there is flow is expanding, velocity will be going outward, right, and I have to draw the arrows correctly. Anyway, I have to remove the jet boundary, and I will change the arrow length to be a little longer. Okay. So this velocity has now increased a little bit, it accelerated along with change in pressure. So if this is the new velocity vector, then the very last set of fluid elements that are coming here will also be going parallel to this. So that becomes your jet boundary. Any fluid that was coming in will be inside this line and a similar line this side. I have to remove my old jet boundary. So, this will be my new jet boundary and the flow velocity is like this finally. This is what you get when the velocity initially like this. Okay. Now again, now since we have discussed the shock problem, I can go a little faster in this time and I am going to say it is going to turn like this and the fluid just keeps going like this till the other set of expansion waves cross this one and just go all the way to the end. As I told before, they are just messengers, they are taking the message that the flow has a lower pressure outside. That information has to go all the way till somebody else says do not change anymore. Till that point it is just going to continuously send this information out all the way out there. Okay. Till where will it be accepted as is? Every fluid inside will accept whatever. Outside atmosphere is very strong, it does not want to change pressure. If I assume that to be correct, perfect, then I am going to say outside does not change at all. So, when this expansion goes and meets this dotted line, these pictures become bigger, that is why I started with a smaller picture at the beginning. Okay. So, this line is supposed to be one straight line, it is just going out like this till this expansion fan first wave goes and touches that. At that point this expansion fan goes and tells that your pressure has to decrease further. Okay. And think about it, this expansion fan is left running expansion fan, which means it wants to accelerate the fluid to the right, it is going like this, it is accelerating to the right, while this is a right running expansion fan, it is going to the right, which means it wants to accelerate the fluid to the left. Okay. Remember that. If the expansion fan goes to my right, I will be told to move to the left, okay, it goes the opposite. So, currently the fluid experienced a right running expansion wave and the fluid turned to the left and it is going like this. Now, it is feeling a left running expansion wave. Now, what will happen? Since it is a left running expansion wave, that is going to go until fluid should have more right velocity or it should have less of left side velocity, that is what it is going to tell, right. So, at the end of it, it is going to go to a point where it becomes straight and even longer velocity vector than that, because it is also expanding the flow further, it is accelerating the flow even more, okay, and it is going to even higher velocity there. Same thing will happen this side. I am talking about this fluid element now, it is first facing a left running expansion wave, which means the fluid is accelerating to the right, okay, and immediately after that I keep going, I have to draw it symmetric also. This expansion keeps going like this, looks like I am not drawing very symmetrically, I will try and match the top one, close enough. And after this point, this fluid element is going to see a right running expansion wave. What does that mean? It is going to get a velocity towards the left. So, it will turn more less to the right and more to the left. So, it is going to finally become this. Why should it become this? That is because the Prandtl-Meyer angle expected on this side is same as this side, okay, that is the only reason. Ideally, if I have different pressure here than this, then this need not be very symmetric, some final flow will be some other direction, that can also happen. Okay. Currently, we are not having that crazy setup, we are having simple enough atmosphere, both sides are same pressure. If I think about a very complex problem, then I can have this pressure different from this pressure and these expansions will not be symmetric, which means this will bend it by some angle, this will not bend it back by the same angle, it will bend it by some other angle, and the final fluid will have some net direction. And you can always expect that because now the jet will not go symmetric, it is going to be tilted to the down if this pressure is more than this pressure. Why? There is a pressure difference across this fluid element. Overall fluid element that is coming out is seeing that this pressure is higher than this, it is going to accelerate down net, right. That is one more way of looking at it. It has to do that eventually. Just think simple logic, it works most of the times. Okay. So, we will not pick that complicated case, we are going to assume symmetric problem, both pressures are exactly equal. I am not drawing it very symmetrically, but it is supposed to be symmetric, okay, doing something like this. So, let us say I won't draw both sides and try to make it symmetric, I will draw only one half. It is the simplest way to get through in engineering style. So, I am going to say I have this compression wave, expansion wave coming here, and now at this point this expansion wave is just telling the outside atmospheric fluid that it has to decrease pressure, but the outside atmospheric fluid is going to say no, I will never change my pressure. That is why this becomes your boundary condition. It is telling I am not going to change, you have to change your pressure. How does it impose it? It forces a compression wave on top of this expansion wave to negate it at that point. It will be exactly equal and opposite value. It will be an expansion fan, a compression fan matching this exact expansion value, so that at that point it is 0 change in pressure. Okay. Similarly, it will happen for all those expansion waves inside this expansion fan. Every one of them will send out one such thing, and a whole bunch of things together will eventually form one shock. It is similar to what we did last time, almost the same concept. It is going to go through this whole thing. Similarly, there will be one more coming from this side, and there will be a shock, and I am going to say these two shocks interact, ideally they should be symmetric, and after this we know what happens. It is two shocks interacting, we will just look at from this point downstream, and I am going to say it is going to go crossing like this. What is happening here in the middle? The flow is just parallel. When there is a shock like this, what happens? Flow turns, if it is a right running shock, flow turns to the right, right. Compression wave is a wave which tells there is too much crowd there, come along with me, right. Think that it is a right running wave, so the shock flow will be turned to the right, going to be turning in like this, and then this is a left running wave, so it will be turned back towards the left and it will go back to parallel, does something like this. Okay. Overall, that is what is happening. I am also trying to draw the velocity vectors lesser and lesser as it goes. Now, if this is the flow vector, my dotted line should go like this, and similarly from the other side, and then now it is going to go at this point, this shock goes and hits this corner. Now, what should happen when the shock goes and hits to that corner? Now, this set of compression waves together have formed one shock, and they are going and telling you have to increase your pressure. Again, the atmosphere is very adamant, that fluid element sitting there is going to say I am not going to change. So, what will it do? It will put how many ever compression waves we have, so many expansion waves at that point, negating each one of those compression waves. Okay. So, finally, there will be a whole bunch of expansion waves traveling from here, and they start going like this. Similarly, from the other side, a whole bunch of expansion waves going like this. Now, they will start crossing, and if I look at the problem from here, it is expansion waves crossing, which is the exact same problem as what I started here. Now, all I have to tell you is, if I draw this line here and draw a similar line here, take this picture between these two lines, take this whole thing, put it after that line, and another after that line again, like this whole structure just keeps repeating one after the other. Okay. This is what is going to form your expansion contractions, expansion compression cell structure. I have drawn one simple case where this kind of reflection at the axis happens. We also know that when two oblique shocks interact, it need not have this simple reflection, right, reflection at the axis, or you are going to think about they are just crossing each other simply. That need not be the case. I may have a crazy situation, I will just start drawing from that expansion turning at the top and bottom, where I am having a stronger oblique shock, and now if my fluid is coming like this and turning very sharply, it may not be having enough energy to turn it back straight parallel. There could be a situation where I may end up with a Mach reflection at this point, in which case it becomes a shock and then turns around like this. Now it will be more difficult for me to draw velocity vectors correctly because it will cross the region. So we won't draw velocity vectors for now. It is going to do something like this. Now what is going to happen? The flow is going to have dotted line like this. This is my jet boundary now. And after that, again there is a shock coming and hitting this boundary, which means again there is this adamant fluid element sitting here which will replace all the shock with full set of expansion fans. So there will be a whole bunch of expansion waves going from here. Same thing will happen from here. Okay. This whole thing repeats again. This can also happen. When such a thing happens in a flow where I have expansion, I will just go back and reconstruct. And I have my nozzle here. If I have my flow situation like this, if I have a case where I have an underexpanded jet and it forms this kind of a shock, typically if it is an axisymmetric nozzle, then what will be the shape of this normal shock? If I look from that side, it is an axisymmetric nozzle, it is like a tube. This will come out to be a circle, axisymmetric again, right. If that is the case, then it looks like a disc, okay. And since Ernest Mach explained this kind of phenomenon of shock reflection or shock crossing, this is called the Mach disc. Okay. This is called the Mach disc. Okay. So if you see books which are talking about underexpanded jets, they typically tell there will be a Mach disc. Okay. There could be a situation where the number of expansion fans is not enough. This is not number of expansion waves is not this small. It can be really high. It can be as high as this is the starting angle, but the ending angle could be somewhere here. I can have an expansion fan all through up to here. Can also happen. Okay. Let us pick such a case. I will draw only the top half and put a center line because I won't have space otherwise. Okay. I am going to draw expansion. Starting will be the same as original Mach number, Mach angle, that you do not have a choice, but the pressure outside is extremely low, that my delta theta will be very high because my delta nu is going to be pretty high. We know you can have, if it is Mach 1.5 here and I have very low pressure here, then I know I can have all the way up to around 120, 130 degrees turn, right. We said if it is Mach 1, then 130 degrees is the best turning angle you can get for infinite Mach number expansion, right. Pressure should be 0 for that, which is not really possible. We also said that when we are dealing with Prandtl-Meyer flow long back. Okay. If I think about that case, I can tell that my angle can be more than 90 degrees also, right. Even if my Mach number is 2, I can have more than 90 degrees angle change if my pressure is extremely low here. So let us pick such a case where my expansion is this wide, this full region is my expansion wave, this is all my expansion fan, everything inside is expansion fan. If that is the case and my flow is turning like this, it is going to turn finally out at some angle like this, that is also a possibility. Okay. It is going to come like this and it is turning and it is turning out. I maybe put too high an angle, I decrease it a little bit, something like this. Yeah, I want to make sure that this to this angle delta theta is same as delta nu. Should be, no, it need not be same as delta mu though, so I am probably okay with it anyways. So I am going to have something like this and it is going out like this. You have to think about the other expansion fan coming from the other side, that is also going to go through, and now remember it is a left running wave. If I think about this particular wave, it is a left running wave. What does that mean? It is running to the left of the fluid element local velocity vector, which means when this thing is going up like this wave comes here, this fluid element is going like this, when this wave comes here it has to run this way with respect to that fluid local velocity vector. Okay. So, it can even turn this way, this particular expansion fan coming here can also turn that way. Okay. Then you will have more complex phenomena happening here when this expansion goes and hits there and tells that it has to become a compression wave. Okay. Typically it is going to hit and come back as a compression wave from there. There will be a whole bunch of compression waves coming. If I think about this as my jet boundary, then it goes and hits there, and then from here there will be a compression wave coming back. Till here it is straight line. This is my first wave I said. Every other wave is also going to go hit and come back. So, my jet boundary becomes something like this. I will use some other color for jet boundary. Let us say I use this whatever orange color for this. Okay. Some such thing. Okay. If I use this as my jet boundary, I can tell that even before this expansion, the top one expansion goes there, this expansion goes and hits there, and I am going to tell that this whole set of, I have to use white now, some other expansion that is coming here is also going to do the same thing, it is going to hit somewhere there, and some other expansion wave that is coming here is going to hit somewhere there. All these starts to happen, and they are going to get this kind of jet boundary and a whole set of compression waves coming from all of these points. Every point from here will send out a compression wave. Okay. When all these compression waves are coming, they are supposed to be right running with respect to that local velocity vector only, which means it need not be going downward. Expansion, when the velocity vector is like this, it may still be running like this, that may be right running for that locally, right. I have just drawn it such that it makes it simpler for you to think about it. Okay. What happens is there is a whole bunch of these coming together along with these expansion fan, this one from this corner going and hitting the boundary. Okay. This is going to hit, at the same time some wave from here has started turning and that is also going and hitting there. Okay. All of them going and hitting, they are all going to start turning there. That will be a little stronger because two expansion waves go and hit, it will come back as slightly stronger compression wave. Whole bunch of them coming together, they will all meet, compression waves you know they come together and they are going to meet and form a shock at some crazy angle like this. Okay. This also happens. When this kind of thing happens, this is going to experience the expansion fan from here also, that shock that is forming. Okay. Because of that you are going to see the fluid turning that way, right, similar to here. Here I did not draw the velocity vector, I will go back and draw it. This expansion is making sure that the flow velocity vector turns back to axis. So, here velocity vector is like this, as it goes through that way the velocity vector is becoming parallel, and the shock is supposed to be right running for that local velocity. It means that the angle will slowly start turning like this as it goes. Okay. So, you will go to a point where the shock looks something like this. Okay. And I have drawn it as if the shock starts here, it could even start from somewhere here, anywhere here, depending on how many compression waves come together, it can be even from here, that does not matter really. Okay. And they are going to have a jet boundary, this is my orange color or whatever color that is, it is going to go like this. Okay. Now, the flow as it is coming along this region is going to slowly turn back to parallel before the shock. Okay. And after the shock what should happen? It will turn back inward, similar to this, but it is just more curved shock. Similar to here, after the shock it is going to turn back inward. That same thing is going to happen in this region, and your jet boundary will also start turning like this. Okay. Now, I will go extend my axis. at the axis for this much of expansion, if I form all those expansions come together forming a shock, that shock is typically very strong near the axis. So, when it crosses the axis, it goes through a Mach disk. I am drawing only one half of the thing, otherwise it is supposed to be a disk fully. Okay. It forms a Mach disk, and this also happens. This is typically a very under expanded jet. Okay. It has to expand a lot after it comes out. That is the case for this. If this happens, then you have one more extra feature which has a special name. Typically this happens when you are having rockets go out in space, that kind of situation when the chamber pressure is so high, exit pressure is going to be matched by the chamber pressure, not matched, it will be proportional to that, and if compared to that the outside pressure is almost vacuum. So, you will have this huge expansion coming and you will end up with this particular feature called a barrel shock. Barrel shock. Why? It looks roughly like a barrel. It is not complete barrel, but it starts somewhere here and it just goes like a barrel for storing liquids. That kind of barrel just looks like that. And at the end it has a Mach disk like the top lid of your barrel or something. Going to look something like that. So, that is a barrel shock. Okay. And this is also one more feature in this flow when this happens. Typically this problem becomes much more difficult to explain after this point, because there is expansions and expansion waves from both sides crossing. While they are crossing, there is compression waves crossing, and it becomes much more difficult to explain this problem. Okay. At this point, if you think about it, there is an expansion wave coming from here, there is an expansion wave coming from here, and there is compression wave coming from here. All that are meeting here. What will be the final result of the flow velocity vector turning? I cannot tell very easily from here. Okay. But if I use method of characteristics for solving this, most likely I can still get the correct answer out of it, if I assume I know how to use method of characteristic really well. Okay. But that is one way of looking at it. I have not given you method of characteristic yet, we will go for it after some time. Okay. So, this is one more feature that happens in this kind of flows. Otherwise it is similar to what you have seen before. There will be this shock structure, the expansion shock cells will be there. I already told you, right, this dotted line, this line to this line, take this and copy it to that side and copy it to one more and copy it to one more, and it just keeps on going like this forever. If that happens, then you will see your expansion compression cells just continuing to happen. Okay. If we recall what we did last class, we said that we will have a jet with first thing will be shocks, and after that we just have expansion compression cells. If you look at it, the only thing that repeats will be from here to here. This whole structure can be put one more level here and one more level here and one more like this. It is always the expansion compression structure that is going to be repeated several times. Only difference in a over expanded jet is it will have this initial portion of some two shocks crossing. After that it forms the other structure and it just goes on like this forever. I will go back here and I will just label these numbers like last time. 1, 2, 3, this region must be 4, 5, and then I can go for a 6 and 7, and it just keeps on going like this. If I think about the pressure at 1, this is a under expanded jet, which means it is more than atmospheric pressure. Under expanded jet, it has to still expand to atmosphere. Okay. And region 2, this and this both are region 2, symmetry of course. Region 2 is exactly same as atmospheric pressure. After that, region 3, it has expanded from atmospheric pressure across the expansion fan. This pressure is lower, and then I go more, there is a shock and it goes to higher than atmospheric pressure. How do I know that it is higher than atmospheric pressure? if I look at this region, these compression waves are turning to this direction, and this region will be close to atmospheric pressure, because that is what is forced by these compression waves. These compressions are going to negate the effect of this expansion on this region. So at the end, after all the compression waves, I will get back to atmospheric pressure in this region, and then I will go for a shock after this, and that is going to be your higher than atmospheric pressure condition. So the whole thing together, I have started from higher than atmospheric pressure, went to atmospheric, went lower than atmospheric, and then went to atmospheric, and then went to higher than atmospheric. If I think about a non-center line streamline, if I think about a streamline that goes like this, it goes like this, goes there, turns down, and then comes back parallel. If I pick such a streamline, then it is doing that. If I pick the center line streamline, higher than atmospheric pressure, during the expansion processes inside here, it will cross expansion somewhere atmospheric pressure, then it will go to lower than atmospheric pressure, high, drops to low, and then stays low, suddenly jumps up to high, and then just stays high, and then it drops to low through this set of expansions, and then it goes low, like that it just alternates up and down. Okay. If you actually do the calculations, you will find that 1 and 5 will have the same pressures, and 3 and 7 will have the same pressures, and it just goes like this. And of course, 2 and 4 are supposed to be close to atmospheric. That is what you will get. Okay. 6 is also atmospheric. Yeah, all the even numbers are atmospheric, and odd numbers 1 plus 4, 1 plus 4n will be something, and 3 plus 4n will be something else. Okay. So this is the overall structure. This same thing you can see even in the over expanded jet case, what we did last class. Even there you will see the same kind of system. Okay. Now I have to talk about one more thing which I forgot at the beginning, that is when I think about a fluid slab that is coming here, like what we did last time for over expanded, fluid slab is coming here. What is happening to it? It is increasing in size. Is that logical? Yes, it is logical, because it is going through an expansion process. Why? Because the pressure outside is much lower. It is trying to occupy all the volume there, because there is nobody occupying it. It is much lesser pressure. Okay? It is expanding and occupying the space. So it is going up. And in the process, it has inertia. I want to think about it as inertia. If you think about, it keeps on increasing so much that the pressure at the center drops. When this happens, then they want to implode, come back in. That is this process. It is coming back in and decreasing in size, and again it went past due to inertia, overshot, and it became very high pressure, and then it is again expanding and contracting, expanding and contracting. In this whole mechanism, there is no process that applies brakes, right? There is nothing that says slow down, you will be reaching there anyway. That kind of thing is not there. But in real life there is something like this. That something happens to be viscosity, okay, which we are neglecting in our gas dynamics currently. In our gas dynamics, I am going to say there is fluid going like this, and the next fluid element here is just sitting idle, not moving. That is not allowed in real life. In real life, that momentum from this last fluid is, part of it is taken and given to this fluid, which means this is also moving, which means energy of this fluid element is slowly decayed out in both sides. It is leaked out in both sides. Eventually, energy is so much spread that the jet is expanding out. The moving fluid, if I call as the jet, there is more moving fluid on the outside now. That is going to change the system also. Okay. This whole sequence of things that happen. When I think about this case, this is very under expanded jet. Why do I call it very under expanded jet? We go back to our pressure picture. I am going to talk about a case where it is like pressure is somewhere way low. So it is going to have a huge jump from there to here kind of pressure. If I jump from some pressure, this is my exit pressure, and I jump from there to all the way to here at outside pressure. Say I am almost vacuum here, and I am jumping so much. Now I have to think about the fluid element that is coming out from here is going to expand from here suddenly to a really huge size, okay, and it is going to expand to something really big like this, going to expand to a huge size. There will be times if you see some rocket flows, you will see a nozzle of the rocket like this and the plume will go like this. That also happens. If you think about what is happening there, whole set of expansion fans going all the way there, that the fluid that is coming here is turning around there. Okay? It is turning all the way out there, and after that this set of expansion fans that are coming here are turning around that fluid back to this direction. That whole set of things are happening out there, and if you have some such case, you will start having compression waves from here itself. It will form a much bigger barrel, start having a barrel shock like this at that point onwards. This happens typically in upper atmosphere. You will see barrel shock with a Mach disk kind of shape in rockets when it is flying way up, and you can see pictures of that in several websites. ISRO website also has pictures of this. If not, NASA website has it. You just go look at those pictures. It's nice to see these. Okay. These are also nice things to observe. Okay. So there is one more thing I just have to tell you about this under expanded versus over expanded, which is when they talk about rockets, when they are taking off from the ground and going all the way up, the rocket is actually experiencing high pressure at the bottom. As it goes up, it is experiencing low pressure. What pressure am I talking about? The back pressure, okay, for the nozzle jet. So if you think about it, the PB is decreasing continuously, which means in my problem I am looking at that in my pressure plot I am starting from up and I am going down continuously. I may not be really starting at PB equal to P naught, I will be starting somewhere down there, but from that point on I am continuously going down. That is what is really the case, which means I will typically start with a over expanded jet to an under expanded jet. This whole sequence happens when a rocket is being launched, which you will actually see if you look at the plume size as you go. When you are beginning, no, this same rocket, I will erase one part of it. Let us say this is the high altitude jet plume like this. The low altitude thing will be looking more like this. That will be your rocket plume when it is taking off initially. It will not be looking very big compared to the nozzle size. It will just be looking, in fact it will contract slowly inward at the beginning, which says that my fluid coming here is turning inward. This is my shock, and of course remember that my plot is different across my center line. This is one picture, that is another picture. Okay. Initially my jet is going to be a very small thing, and when the pressure outside is decreasing, the jet expands to fill the space, and that is what you will see out here. Okay. This whole thing starts happening. Okay. Now when you talk to people, they will say that the pressure is decreasing. Why are you talking about going from over expanded to under expanded? Shouldn't it be the other way? It is just a confusion. But I told you last class also, again I am repeating this, over expanded or under expanded is with respect to the fluid element at the exit of the nozzle. Is that fluid element already expanded to the outside pressure? That is what we are asking, that is the question we are asking. Okay. When the pressure decreases, we are going from over expanded to under expanded. It is confusing. That is what is the typical confusion to actually only the undergrad time. Okay. If you think about it, what we are talking about is pressure outside is decreasing, which means initially pressure was very high compared to this pressure, which means I have expanded too much this thing, this fluid, so it is over expanded. Later this pressure decreases, and so I end up with this picture. Then I have expanded too little, I have to expand much more after I go out, so it becomes over expanded, sorry, under expanded at that point. Okay. That is what happens out there. How many such expansion compression cells can I have really? how many such expansion compression cells, this repeatable packets, how many will I have in a jet? Ideally it should be infinity, right? If you think about it, it should be how many ever number, it should just be going oscillating up and down, up and down, up and down forever. I said ideally because we have neglected viscosity. If there is viscous effects, then depending on the velocities, if the velocities are very high, viscous effects will be much stronger. The velocities are very tiny, the velocity need not be dissipated so well. And so depending on how the velocity effect is in this case and whether the fluid here is already moving or not, that kind of will change the answer. Okay. It so happens that in a rocket the fluid outside is moving already, because the rocket wants to go up, the fluid is going down with respect to the rocket, right, and the jet is also going down with respect to the rocket. We need to fix some reference, I will fix the reference to be on the nozzle. So everything is going down with respect to it. So the velocity difference need not be very high, typically there will be some difference. So there will be some difference in velocity, the jet will be higher velocity than this. Okay. So there will be some effect of shear along the edge of the jet, that also happens. We have not talked about viscosity affecting the gas dynamics of the problem yet, okay. But we will try and avoid the gas dynamics part of it, and we will try and explain how a shear layer has effect on the flow itself, say one more class after, or maybe next class itself a little bit we will talk about it. Okay. Just wanted to give a glimpse of how a supersonic shear layer looks like. Okay. Just it is fun to explain something like that, it is nice to explain that, that is the only reason why I will go for that. The next thing I need to start is solve a numerical example of a problem like this, not really this type. I believe I picked a problem where we are in this kind of situation. Okay. We are picking a case where it is over expanded case. So we will have a shock at the beginning, okay. Over expanded case. I am picking a nozzle and I am going to go through the solution of this whole thing. Till where can I solve this problem? Can I solve this problem all the way? Looks like I can keep on solving this problem all the way. It so happens that it becomes complex when I have to think about there is a set of compression waves and they start forming a shock. Okay. At that region the problem becomes not simple to solve, and we will not solve after this point, we will solve till here, we will not solve any more of that. Okay. We will try and solve the problem up to this point. Okay. We will see how well we do this. Okay. What we have to do is, let us just go through the thing, I do not want to talk too much. I am having a P naught of 80 bar, something close to what typical rockets had some time back, and I am having exit Mach number as 2.0. I am picking such a nozzle, exit Mach number is 2.0. So I want to find a pressure where it is over expanded, back pressure I want to decide. I am choosing my rocket to fly at different altitudes, I do not know what atmosphere it is, I am just going to pick some case. So I am going to say let us find a value below P critical 2 and above P critical 3. For that I need to know P critical 2 and 3. So P critical 2, how will I find that value? To find P critical 2 I need P critical 3, right, because you need to know the supersonic pressure and then multiply it with P2 by P1 at that shock. So P critical 3 we will find first, that number is related to P by P naught at that exit Mach number into P naught currently, that will be the pressure at the exit if it is fully supersonic, that is your critical pressure 3. That value, for assuming this gas to be air, gamma is 1.4, we get to a number 1.024 bar. Okay. This is the number we have. This happens to be your P exit for this condition, is that right? because Mach number is 2, there is no shock inside my nozzle till that point. That also happens to be equal to my P exit for my nozzle. Now I will go for P critical 2. Now I will take P critical 3, multiply by P2 by P1, where shock Mach number is equal to exit Mach number. Okay. This is the only change I need to do, and that happens to be 1.024 into 4.5, which is 4.608 bar. Okay. These are the numbers we have. Now I want to find, now I want to choose the problem. I am going to pick some back pressure. I have to pick something in between these two for me to solve a overexpanded nozzle problem, overexpanded jet problem. So I am going to choose 1.5, okay, which is close to almost expanded kind of condition. I did not want to have a Mach reflection here. If there is a Mach reflection, it is difficult to solve. So I chose a case where I know is closer to P critical 3. So I am picking 1.5. So I am going to say, I am going to solve a problem PB equal to 1.5 bar. This is the problem I want to solve. So how do I start? The first thing I need to do is find the beta of the shock such that the pressure downstream is equal to 1.5 bar. That is the idea of this shock, right? It is supposed to have an angle such that it corrects the pressure of the fluid to outside pressure. That is the job of this shock. Okay. Previously we used to do this flow angle turning as the boundary condition. That is a simple thing. I told you gas dynamics has two things. One boundary condition is pressure, other boundary condition is flow velocity vector direction. In this case it is not velocity vector direction, it is the pressure. Okay. So I want to match the pressure. So how do I do this? I have to first guess a beta value, and then I will go through the calculations, and then I will find what is the pressure here. Then if the pressure is lower, then I will increase the beta so that it is more normal, pressure will be higher. Okay. Or if the pressure is too high, I will decrease the beta so that it is less normal, so the pressure goes down. That is the logic. What should I start with? What beta will I start with? Is there a range of betas which I can use, or can I use anything from 0 to 90? What is that? 14 degrees. What is it? 40 degrees. Why 40 degrees? Is there any reason to choose that? Is there any limit on the beta value I can use? Can I have all beta values for any particular case? What is the problem? Where is the problem? You have to remember your oblique shocks now suddenly. So what I have to think about is this. I will draw this picture and suddenly you will know the answer. What will be my beta values? Weak part of this is one thing, but what beta values can I choose? Is it 0 to 90? What is it? Mu to 90 degrees, that is all I can choose. Okay. It may so happen that I may have a solution in the strong side also, but currently we will say that it is only weak solution that happens. Okay. So ideally I have to guess somewhere between here and the weak. Okay. Let us say I will choose something close to this weak, the mu value, so that things will not be very wrong. What is the mu value for my Mach number? Mu for m equal to 2 is what? That you should know. 30 degrees. Okay. Sin inverse 1 by 2. Yeah, you should just know the answer to that. Okay. Sin inverse of 1 by 2. So now I have to go through this iterative process, which I don't have time for today. Iterative process goes for like 5 columns and so many rows. We'll do it next time. But I have to guess something close to this because I know my final answer is supposed to be close to Mach wave instead of oblique shock. Right? If it is a Mach wave, then my pressure will be 1.024 bar. That's my P critical 3. While I chose a 1.5 bar as my back pressure. So I want to choose something close. Let us say I will choose 40 degrees, 50 degrees, that kind of number. Start from there, and I know the answer should be somewhere between say 50 degrees and 30 degrees. We want to work through that with iteration and get to the answer. I know answer is definitely more than 30 degrees. So you have to see what should be the answer for this. That is not enough. Immediately after that I have to also find what is my jet boundary line. The picture I have drawn is not correct here. If you look at it, the jet boundary goes and the shock goes past that. That is not right. Okay? But anyways, we will draw a better picture tomorrow or next class and we will figure out what to do. Okay? This is the idea. Now you just have to go through guessing betas, getting the pressure after the shock and try and match it with the back pressure. That procedure we will go through next class. Then we will see if we can go to supersonic shear layers also next class. Okay. We will stop with this for today. See you people next time.